Hey, welcome to this video number 2 on which we're going to talk about the specific wind called thermocirculation wind that is in fact blowing because of differences in temperature between two places. So going into that detail, that in fact is a wind that happened quite a lot, and we'll see a lot of examples from that type of winds. What happened is in different regions, some places will get warmer than other places because of maybe receiving more sunlight, the type of cover on the surface that may be different. At the end, what we observe is a place where that will be warmer. And so we saw that as a place gets warmer, the air is in fact getting less dense, lighter, and so it starts rising. It's creating buoyancy, or if you prefer, convection, as we talked before. And so what happened is we have a change. We have this air moving up, and so we're creating on top of this part a high pressure system right here. On the ground part, because the air is leaving, it's kind of creating a vacuum. We have a low pressure system on this side. So we're forming a low pressure there because the air is leaving, and a high pressure on the top because the air is arriving and accumulating. On other places, because of maybe lack of sun, different kind of cover, the ground will be colder. What happened is at this point, the air being colder will be more dense, and so it will start sinking. It will be heavier, creating now a high pressure on the bottom ground, on the bottom of the ground, on the ground, because all the air accumulate into the ground, and above we are creating a low pressure because the air is moving away from the higher part of the elevation. And in fact, what will happen is naturally the air is always moving from where you have a lot to where we have less. It's in fact the case for, it's a general chemistry case called Le Chatelier, where we're always moving from where we have more to where we have less. We saw that with the heat transfer, where it's getting warmer to getting colder. Well, the air will follow this. And so it's moving from where we have a lot, which is a high pressure, towards where we have less, which is a low pressure. So we start seeing, in fact, creating these loops that communicate together, where low pressure will create a high pressure aloft and connect to a low pressure aloft that sync to a high pressure and join the low pressure. And so we're creating an air motion system, which is in fact what we call a thermal circulation. And so we observe, based on that, the thermal high pressure and the thermal low pressure that will be happening in this system. And we have a different kind of example. Sea breeze, land breeze, monsoon, mountain and valley breezes are all different type of thermal circulation winds. Quick notes on the motion of winds from high to low pressure. This is driven by a specific force, which is called the pressure gradient force. The pressure gradient force is in fact this force that make the motion of the molecules of air from the high pressure towards the low pressure. And you always go from the high to the low, then it's going straight forward. And usually, if you have an isobar, it will always cross the isobar perpendicularly, meaning that isobar, remember those lines of same pressure? Well, if you look carefully at this, the way we present the force of the PGF, pressure gradient force, they will always be perpendicular to the isobar, okay? The same here. And so the isobars are, the PGFs always moving away from the high pressure and going towards the low pressure. So this is a driving force moving the air from the high to low pressure. If we apply that to different regions of the world with specific characteristics, we found in fact some specific local wind. So we're in mesoscale, meaning that we are between a couple of 1,000 meters to a couple of 100 kilometers, more or less. We can talk about the katabatic wind, which is a specific wind found usually in high latitude with a cold air and high elevation. Usually this happens when you have a topography such like that, where you have a high plateau, so like a mountainous region, such as Rockies or Rocky Mountains or mountains in Canada, for example, you need to be in a colder condition, and some land that is in lower elevation. And what happens is you have a high pressure system usually that will establish itself above the mountain and a low pressure on the plain. And the wind will in fact follow the slope going from the higher elevation to the lower elevation. The thing is, this katabatic wind is particularly strong because there is not too much vegetation, as you can see, because it's mostly covered by snow or ice, and also it's bringing very cold temperature, as you can see, of between a -4 and a -25 degrees. So we are really in a higher latitudes, again, Canada, Alaska, Arctic, or the major katabatic wind we observe on Earth are in Antarctica, where we have the good condition for it. We have a cold temperatures. We have some good elevation. Katabatic winds can go faster than 200 miles per hour, so it's pretty quick. Oh, sorry, not 200, about 100, 150 miles per hour. I'm a bit too fast. They can be quite destructive, and they covered everything with snow that they carry along. And this is driven just by mostly the pressure gradient and also the slope that accelerate that wind. More locally, if we come back to California, we have similar winds that are called the Santa Ana winds. Those are winds observed mostly in South California, generally between October to March. What happened is during that time of the year, we tend to have a high pressure system above California, kind of a high pressure system that establishes itself above the mountains surrounding South California. So the Trans Mountain and the Transverse Mountain and the Peninsular Mountain. The high pressure system is right here. And on the sea, we have a low pressure system, usually that tend to be on the sea. And so you do have a pressure gradient that goes directly from the high pressure to the low pressure system. Those winds are very particular for California, again, because of this configuration, but because they also happen during October up to March, they tend to be, in particular for when they occur during October, November, they tend to be amplifier of the wildfires. Usually during that time of the year, there is some wildfires happening in the foothills of those mountains, and those Santa Ana winds will be blowing and amplifying, increasing, enhancing those wildfires, also helping those wildfires to move to other places. Those winds are quite dry because they're coming from higher elevation, they don't have humidity, and they are in fact just like if you're on your grill doing a barbecue and just had adding some air on the barbecue, you can see the flame, and it's exactly what's happening, making those wildfires even stronger and more difficult to contain. So this is more an example of local wind that we can find in California. We can also find in California, around the mountain, what we call the valley and the mountain breeze. The valley breeze will happen during daytime. During daytime, particularly during the morning time, the top part of the mountain will be warming up faster than the bottom part and the valley in itself. So you're creating a low pressure system because the air getting lighter will start to rise up. And at this point, you will have a low pressure, and you can consider the valley to be colder, to be more like a high pressure system. And so naturally, you will have the air moving from the high pressure system to the lower pressure. And so you have an air that moves uphill. And this is usually creating clouds. And we tend to observe clouds during the morning, midday time above the mountain. Then at night, the contrary happens. The sun moves, the sun disappeared from the picture, and the top part of the mountain gets colder faster than the valley in itself. And so we're reversing the high and low pressure system, with higher pressure system being on the top part of the top part of the mountain. And so at this point, the mountain breeze happens with, in fact, the wind blowing downhill, going towards the valley and bringing, in fact, cold air. So at that time, we don't observe, in fact, of course, clouds because you do not go into condensation. But that is a typical breeze that we tend to observe in the mountain, the valley breeze in the morning, the wind that goes from the valley to the top part of the mountain, and at night, the mountain breeze where the wind comes from the top part of the mountain towards the valley. Then, if you're living closer to the sea, and it's happening, of course, also in California, we have what we call the sea breeze and the land breeze. With the sea breeze and the land breeze,
A sea breeze takes place during daytime.
Up quickly. I'll just go back into the video in a bit. The sea breeze and land breeze also happen between the formation of high pressure system and low pressure system. We do observe a high pressure system that is being creating over the sea during the daytime and a low pressure system happening during land over the land during daytime. The reason why is during daytime, the sun will warm up faster the ground than the sea, just because ground, the soil, warms up faster than water. Water takes more time to warm up. And so naturally, the air above the ground will start rising up. And so we start making this convection. And very much like we saw initially with the thermal circulation, on the sea, we have a higher pressure system down on the sea level. And so we're creating a loop. And as you can see during the daytime, we observe what we call a sea breeze, the wind coming from the sea into the land that tend to, in fact, cool down the temperature of those places, of the land. This is something that explains why San Francisco tend to be colder than the inside of the land, because it's receiving the fresh air from the sea, also kind of pushing towards the formation of fog a lot of times. During nighttime, we have a reverse happening with a high pressure system established on the land and a low pressure system that's happening in the sea. The reason behind is with the high pressure system on the land, it's because the land cools down faster than the sea. In fact, land changes temperature faster than water. And so with that, we observe what we call a land breeze, where the wind is blowing from the land towards the sea. And I'll play the video now to give you a better explanation than what I just did.
A sea breeze takes place during daytime, and a land breeze takes place during nighttime. As already observed in the earlier slide, a sea breeze happens as the sun heats up water and land, but land heats up faster than the water. So warm air above the land starts to rise, and cooler air from the sea comes in to replace the rising air from the land. On the other hand, a land breeze, like we have seen, happens at night, and this time the sun is gone and cooling has to take place. But here, what causes a difference is that the land cools up faster than the water, and what happens this time, warm air will be rising from the sea and cooler air will be flowing in from the land to replace the rising air over the sea. The cycle also continues, but this time it's in the reverse direction of the sea breeze. So I hope you have understood what a sea breeze is and what a land breeze is. See you again in the next lesson. Goodbye.
Okay, with this visual, I hope that you got the concept between sea breeze and land breeze, because we're moving towards the same concept but over a bigger scale, talking about the monsoon, which is in fact a sea breeze and land breeze happening not on the daily time but on the season time. This is mostly happening over Asia, in particular India in itself. We do observe a monsoon in fact that here in the US in particular, what's called the Arizona monsoon, but it's a lower intensity one. And I will only focus for the major one that we observe in Asia at this point. During winter time, what happens usually is you have a high pressure system that will happen, that will occur over Asia, and the low pressure over the sea. And so during the winter time, we have the phase of what we call the winter monsoon, where the wind will blow from the land towards the sea. Okay, it's very much like during the nighttime. The reason is during winter time, the ground will be colder than the sea. So let me place it. So that's winter time. So the land is cold, the sea if you want, maybe we can say cool. And at this point, during summertime, we have the land warming up faster than the sea that stays cool. And so you're creating the equivalence of a sea breeze, which is in fact the summer monsoon. And the wind will blow from the water to land, bringing a lot of humidity, bringing a lot of precipitation. And that's where we observe the usual monsoon with a lot of flooding happening and people and those regions receiving a lot of water. And there you have also a visual explanation of it.
Warm air is less dense than cold air, and when the heat rises over the Indian subcontinent, the air also rises. A huge area of low pressure forms, creating a vacuum effect and pulling in much cooler air from the southwest. It's at this point that the dry northeasterly winds from continental Asia are replaced by southwesterly winds, loaded with moisture from the surrounding Indian Ocean. This is a southwest monsoon, the abrupt change from a dry season to a wet season.
Okay, and to end this video, I invite you to look and to watch this review that kind of go and summarize those local winds, providing you visual explanation of it and in some way a summary of those different winds that we talked about. Okay, with that, we are done with this first video. Oops, and we're gonna with video number 3. Let me go back to my slide. With video number 3, we're gonna talk about more the global wind circulation. So we've been moving from the mesoscale going to the macro scale to the global scale. Okay, see you in video number 3 then.